Okay, today in lecture 26, I'll finish chapter 16 on the theory by deriving for you the one-third scaling law that we observed in experiment. I'll say something about why we think there could be a delayed wall slip. At the end, I will indicate how to understand the EDT, the entanglement-disentanglement transition.
Had last time. Well, a few days went by, so you may start to forget. But basically, we are looking at just three ways of deforming the polymer, entangled polymer, and there are a variety of instabilities, if you like to call, or strand localizations, if the disentanglement is localized. So these were just a few examples of when you can have that. And if we look at the outline again, we are in the middle of finishing the discussion of in chapter 16. So we had the two model discussed. We talked about all the three forces, and we are now marching on to say a little more in detail about the forcing balance under these two conditions. According to the book, this was discussed first, actually. So I will try to follow that order. And then a major focus today will be for the second topic. It talks about one-third law. And if time permits, we'll continue to discuss wall slip and EDT. Okay, so I will first indicate this was what we sort of had in mind. Let the red chain be the test chain. The buildup of retractive force is due to the gripping force from other chains as you do either shear or extension. Now, I plan to skip this part about some papers and communications I had with Dejin on this topic. So, but I don't plan to say anything about it. So let me just try to bring you to the next thing I want to say, which is to follow the book. And we had one was on tube model, two was on the three forces. The three forces. And third, according to the book, is a small discussion on the step strand. So I will first describe to you about the forcing balance in step strand. So it has a different title there. It's okay. So basically, we had our chain being stretched, any of the chain, which is a test chain being stretched like this, and all of a sudden, if you talk about after step strand, in either shear or extension, all of a sudden you stop deforming. So the termination of deformation means what? Means this gripping force is no longer displacing the test chain anymore. So there is a sense that you can say this gripping force is turned off. Okay? If it's turned off, you necessarily will induce force imbalance. So even the, if you are still deforming, deforming, then the force imbalance may not have occurred yet. In other words, as long as this gripping force is larger than the building up retractive force, molecular deformation will continue. But if you turn it off, then you are presumably also turning off the gripping force. In that case, it seems obvious that you will induce force imbalance because there's plenty of retractive force in this chain, and there's nothing to balance it. Well, not there is nothing. I suggested that there is still some force to balance it, but it's only of the magnitude of this cohesion force, which I believe I argued already in the previous discussions. Let's make sure we have it here. The third force, this cohesion force, is really just on the order of, let me just write it down here. It's really just on the order of the so-called entanglement force, which is really just, by scaling, it's just kd divided by the entanglement spacing. So bear with me. So I basically made a claim that this is a force of a magnitude not very large, kT divided by entanglement length. Well, this requires you to recall what is your retractive force. In the fine deformation limit, it is exactly this magnitude times gamma, if it's shear, times lambda minus 1 over lambda squared, if it's extension. So as soon as these guys are larger than 1, you will have force imbalance. Right? Because you build a force larger than this intensity. Yeah. So that's when we envision that now the perplexed question is solved. The termination induces force imbalance because termination means you withdraw the intermolecular gripping force. So the retractive force just have to fight with this virtual force. This virtual force of only a magnitude of this much. So it can win as soon as you deform it enough. And that's why we see the non-quiescent relaxation and also the filament breaking up. We talked about the conditions for the localized disentanglement to produce instabilities. So I don't need to go into more details on that. And just to get you updated, after the book, there is one simulation studies trying to demonstrate after step strain whether there could be chain instabilities taking place. And it is, at least according to this study, observed that the stretched chains the stretched chains will retract, but it will retract on time scales longer than Ross time. So there is some barrier that suggests it's not a very free Ross retraction. And apparently this retraction may not occur homogeneously as a consequence, they do observe motion after step shear, after shear cession. All right. That's done, meaning we're done with the topic of basically what happens upon step extension or step shear. Generally, we call it after the step strain. Remember, this was the most fascinating aspect of the experimental findings, but now it's quite straightforward why it happened. The termination induced forcing imbalance. And we argued in the limit of B over H not being small, you can have this horse race producing a winner. In other words, some layer will disentangle first, the other layer will not. And then consequently, you will have the system taking advantage of that breaking layer and start to recoil microscopically, producing the motions. So we have a fairly good understanding of that now. So with that, we can move on to section 4. It has the title of basically dealing with the startup now. So this is the part that we're going to focus on today. And first, look at this picture here. It's almost a reproduction of what I just showed you a few minutes ago. Again, looking at the looking at the red chain, with other chains pulling on it through uncrossability, right? This is all produced by uncrossability. Because the chain in moderate deformation will not break. Okay. So in this part, there were again two components, and there is a part of extension. Sorry, there is a part of this startup that involves relatively small or relatively slow deformation, the so-called Rawls-Weissenberg number smaller than 1. This is the limit where chains does not have a lot of chance to stretch. Can be understood, at least empirically. Indeed, in this limit, for example, the maximum is reached rather quickly. It reaches around gamma of 2 or so. And at least from the preliminary considerations, this force is not very large. So let me just call it negligible. And then what is driving this deformation is largely just the cohesion force, which means you can produce a level of retraction not much bigger than the cohesion force. Okay, that's why the yield occurs at a level not much beyond gamma equals 1. So I will assign this as reading. You can read that little paragraph on this section. I will not say too much about it. To us, it's understandable that you will still have a point of yield and force imbalance. Simply because what? I showed you once that this being 2, watch, this being 2, could, in the limit of Weissenberg number being much larger than 1, but still Rawls-Weissenberg number is smaller than 1, this being 2 through this expression means it still occurred at a time that's much shorter than tau. You see the point? So this is a very interesting window where the disentanglement or the forcing balance did not occur through diffusion. That would take much longer time. It occurred still much earlier than tau. Okay? So that's a subtle part. I refuse to do a lot more about it. Let's focus on a case where it was interesting to, I think we just call it 4.2. It was interesting to find out whether we can understand in this so-called elastic deformation regime, this yield strength is known experimentally to go with the shear rate as 1/3 power. Okay, so if you plot your stress as function of gamma, then basically you will reach a gamma peak, and that gamma peak scales with the applied rate to the 1/3 power. Something we discussed in enough detail in chapter 7. So let's make an effort to see if we can come up with some scaling level understanding of why you arrived at 1/3 power. And the way I would proceed is to imagine about this pair of hairpins or this junction. This junction is very effective when we first start to deform because of uncrossability. Over time, if there is time to consider, over time, this chain will start to relax. And how soon does it relax? Well, of course, the relaxation is faster the shorter the scale is. So I have tried to identify in this junction a scale of hairpin size, HL. Okay? So this HL has a maximum value when it approaches the entanglement spacing, which is L and ET. We know by definition. Okay, so that's that would involve the entire strand. The assumption I can make is that the strand basically of this is relaxing on the scale of tau r. So that was the conjecture, the insight we had. And therefore, one can speak about the relaxation on the smaller scale of LH. What is the relaxation time for this strand of LH? And a trivial way I could do it for you is to think that this time is proportional to Rawls time, and through this through this dependence. And so this insight is discussed more in the book that I will not repeat. But basically, you can appreciate that this time scale scales with the size squared. And also, the basic unit of that is the Ross time. So with that in mind about how dynamic the structure is, we can start to use scaling to speculate what is the grip force, intermolecular grip force. At the scaling level, this force can be just written down as kT over LH. So that's very handy. I don't have a full theory for this. I'm just doing scaling here. Okay? So that's the magnitude of force you have. And you can see as t equals 0 is when startup deformation starts. So there is a beginning point. Okay? There is always a beginning point. Everything is referenced to that. After that, your chain will start to relax, and this L will start to increase because it will start to relax over time. And as this starts to increase, F, gripping force, will start to decrease just by definition in this scaling. Okay? So when the force, grip force is still available, what it does, well, it can stretch. It can stretch your test chain in the middle here. So that your test chain will start to build retraction, which is, of course, given by what we already know. It has the amplitude of the entanglement force. And then let's take the case of shear. It grows linearly in strength, and therefore linear in time. So far, so good. You could, for your convenience, do a little bit for now by multiplying a tau r and divide by a tau r. So what you achieve is you can have a Ross time there, and then your time is expressed in the unit of Ross time. Not much at this point. So mentally, this scenario works as follows. We imagine that your grip force over time is declining because of what I said here. Okay, as it relaxes, it loses its ability to grab the chain. It's quite natural and reasonable. How does this thing do? This thing grows in time. So you can claim, it's okay, it went to the play mode. So you can claim, it's very, very, it's a very, very simple picture. You can claim any time prior to this point. You can see, by definition, any time prior to this point, your grip force is larger than the retractive force by the samaj, by the vertical distance between them, right? So you stretch. So your blue line keep growing, until the point where the declining gripping force meet the growing retraction force. So that's the yield point. Or the point of force imbalance. Why not? I did well. Or the force imbalance point. At Ty. So what is Ty? It is when God, this thing just keep twisting. When you reached a particular H, at which LH is of a magnitude that you can solve if you know what this time is, this yield time is. Right? The fact this is a function of time, the gripping force is a function of time, is because your relaxing hairpin size is a function of time. In the inverse direction, of course. So your hairpin is growing in size as time goes by, and the force drops as a function of time. So at this yield point, the two forces are identical now. On one side, you have retraction force, and that's just the entanglement force, Wi at Ty over tau r. On the left, or rather, this force equates the grip force at Ty. Which, by definition, okay, is given by Kt. I'm going to rewrite it. L entanglement. I'm just rewriting it. Remember, this is the definition. So I'm just going to add a L entanglement upstairs and L entanglement downstairs. The reason I do that is you know that this, oh God, I don't want this color. Shoot, see, it happens again. This is a small file, it still happens. Yeah, not too much. Better save it. I just try to undo. When you undo, you risk the chance of crashing. Okay, it's saved again. So let's not do it. So we have it here. And the reason I do that is because I know that what is that? That is just the elementary cohesion force. And then I have this ratio. This ratio, according to this expression, is nothing but tau r over tau y square root. Okay, I'm just using this previous expression. So, and the result is very neat. That's why I'm kind of pleased with this result. You followed, right? So, because this cancels that. Okay? What's left is something just very, very straightforward. In the next slide. WIR is tau Ty 3/2. Okay? In other words, at the point of force imbalance, we call it U point. It is given by given in terms of Ross time, and the higher the rate you apply, the shorter it is the time compared to Ross time through this scaling. With this, you know gamma y is nothing but gamma dot times tau y, Ty, and if I multiply a tau r divided by a tau r again, I have Wi r and T tau r. Bring this in here, that's Wi r 1/3 power. Amazingly, it just shows up like that. So this is not a theory, but this represents certain concept. And the concept is in here, in the uncrossability and how you treat the effect of uncrossability. And the way we treat it is this uncrossability produces a gripping force. I just want to indicate that this 1/3 scaling is formally argued in this manner. In particular, it is argued it's argued through this speculation that the force level is determined by the hairpin size through this familiar entropic force scaling. And generally, this force scales with T as -1/2 because this scales with time as 1/2. So you have this expression here that I showed you. This is the way that we can understand that the reason this force is dropping is because this factor is growing, and it's growing as the square of that variable. Or if you like to think about time, then it is dropping as factor of t in the sense of t to the -1/2. Okay, because these two are related like that. Related like that. So, because this thing has 1/h and this thing are related through linear dependence. And then the retraction force is very straightforward. It's just always linear in t. And the slope of that linearity is the Ross-Weissenberg number. That's why you have different slope. That's why I draw for different chains, for different applied rate, they will intersect at different times. For example, when the rate is getting higher, it's going to intersect at lower and lower times. That's all. And you can even imagine a point where the rate is 1, And that probably is going to consume as much time as a Rao's time. So that's all. So this actually, this more well-motivated scaling argument is actually all recognized in our initial paper. So just by looking at the experimental data, we already know our conceptual gripping force is a decaying function. So this is from that original paper, 2007. We don't have the beautiful scaling that I just showed you, but we already know that the magic of this is one is decaying. So initially there's infinite amount of force available to you because uncrossability, nothing can overcome it. But as soon as you start to relax, your ability to have that force is dropping. So that's, so this both figures are in the paper. And we speculated based on data, it was what? Based on what data? Based on this data. So this data exactly, by speculation, indicate that they should have this. So the rest is all history, meaning it's all, that's why I said most of this is already well described in the original paper. Any questions? Good point. So, you can think this way, the simplest. You can imagine that a strand that I just depicted as LH. If you really wait for a time that's specified this way, this very black strand, if it relaxes, it could start to look like this one. Over this tau, over this, over this tau h time. And if this black chain relaxes to that direction as the blue chain, they will not be able to grab each other very well. Right? Meaning it will not be very tight anymore. If all of a sudden you want to grab it, I give in. I also bend it in your direction and go with you. Or something of that. So I don't think I have anything more insightful than this. Except to recognize that this little junction will not be very tight anymore. So, so that's that. And one last thing I think is very useful is for us to really appreciate a little better about the limitations of this account, of the scaling account. This limitation is a entropy argument, the chain conformational entropy argument. You may ask yourself in a different way. So suppose this is what you were proposing, and you were pretty successful in getting the 1/3 power law, right? You ask yourself, as I was saying here, does this gripping force really diverge? Well, as I draw here, right? I draw the diverging. T equals 0, they will be diverging, right? It'll be infinite. But of course it's not infinite. Not only it's not infinite, you will ask yourself, what is the maximum in this argument? What is the maximum? Well, that's the same as asking how small can this be? What is it? Come on. What scale do you have in polymer physics? There's packing length and there is what? Yeah, that's it. That's it, cone length. So I'm going to play a little trick. Have a cone length up and down. Okay? And I just want to have the book notation right. Well, there's nothing right about that book notation. In fact, it's the other way around. So I'm basically going to do the reverse, saying that the maximum in this scenario I can have, call it max, whatever you want to call, is KT divided by cone length. So I'm going to multiply a entanglement length, entanglement length up and down. Okay, so let's just go see. And then you get this. So basically you get the entanglement force. And then this. You know what this factor is? Our dear friend, we see it many times already. It's Q, or it's the lambda max, the lambda extended. Or better yet, it is square root of NE. The number of cone lengths per entanglement strength. Same, right? Yeah, because that's just treating this as Gaussian chain. Treating this strand as Gaussian chain. Well, let's appreciate what that is. First thing first. I think I am. I try to be careful here. Oh Lord. I can only do it in backward, actually. That is, so it turns out I call it F0. And this force, maximum, let's call it F0. I don't know if it's in the book, so I don't have to make a mistake, or I can just venture to depend on how much time we have. It's completely trivial, is what I mean. You have KT, which is 1.36 times 636 or 38. I can never remember clearly. The Boltzmann constant times 300 degrees and divided by cone length. Cone length is about 1 nanometer. Okay, so 10 to the minus 9. So that will knocks down 21, about 12. So yeah, exactly. So this is on the order of a few, let's say 3 piconewtons. Okay, F0 is 3 piconewtons. And the entanglement force, pathetically, is 3 piconewtons smaller by a factor of NE. So we know that's typically a factor of 5 smaller again, because I remember this thing typically for many polymers is on the order of 5. So in any case, both forces are pathetically small. This is less than 1 piconewton, and even this F0 is only a few piconewton. Okay. When I say only, I really mean something very remarkable. Not very much, because for the chain to break, the force involved is several, let's use 3, is 3,000 piconewtons. So there's a factor of 1,000. Got it? And this is where I become desperate when we treat the problem of when we treat the problem of melt rupture. So I want to give you a connection with what we talk about region 4, melt rupture. The phenomenon, you know, it's basically a piece of untangled melt. When you stretch, in uniaxial extension, in uniaxial extension, oh Lord. Usually under, if it's way above TG, you need this to be on the order of 10 or so, or higher. It ruptures. The sample just, upon stretching, just ruptures as if it was cross-linked. And it was pretty clear there was entanglement. Lock up. And leading to transition, which implies you build chain tension of the level of 3 nanonewton, not 3 piconewton. So where did that force come from? Well, the zeroth order story is the scaling argument based on entropy concept breaks down completely. This is why I could not go anywhere further. So you could have region 3, where we could still envision of a retraction of a gripping force being entropic in origin. But pretty soon we get into trouble. Even you force yourself to speak about cone length, which is all there is in a coarse-grained model of polymer chain dynamics, you are far from reaching the condition for chain to break up. So that's where this whole scenario breaks down when you want to treat this region 4 melt rupture. So clearly, when you are stretching fast enough, not only do not have enough relaxation, but also that this uncrossability really is unbound, meaning the force indeed diverges. That cannot be argued with this expression, diverges to the point of meeting. So, if you like, it is also a gripping force, and this other force all the way reaches a point of brittle force even. And the question is, how do you think about that intermolecular uncrossability force? Well, that's where we did simulation. We basically find that there are just other chains that are going to that are just going to tug of war. Remember I said that are just going to pull on the chain so that the uncrossability remains active. Remember, this is simply beyond the scaling argument here. And the simulation was just trying to visualize how could this be maintained. But apparently it can be maintained just because there are enough of the chains that are grabbing onto this chain and hold and deform. So, yeah. So with that, we are at the end of discussing this part of force imbalance, for example. We can move on. I perhaps want to just, the next two topics are rather straightforward now. So, for example, of course, we can now understand this delayed wall slip problem. Remember, this was suggested to be looked at in after the summer of 2006, fall of 2006. Why? Because at that time, the idea behind the JCP paper is already formed. We already have an understanding of how shear scission could induce force imbalance. And then, of course, this imbalance could also occur involving entanglement of tether chains with, oh Lord, tether chains with the untethered chains. So you stretch, which is fine, because when you stretch, your black chain is getting hold of the red chains and stretch. And then when you stop, nothing stops, if it's deformed enough, nothing stops the red chain from trying to disengage with the black chain through disentanglement, through the force imbalance. So we predicted that this must happen. This must happen upon stopping. If you don't stop, there's no wall slip yet, because it hasn't reached the force imbalance point. So this whole idea is about the scission turns off the grip force. So that's the insight. So look like today I can finish much of this chapter 17 before the end of it. So let's see, I'm not going to do, yes, 6 is just about long chain branching that you can read through it. Nothing very quantitative. Just so then, lastly, the EDT. Remember, this is a creep test. We're watching live the shear thinning. Since this is such a common thing to think about, shear thinning, or if you like, speeding up of the sheared system, sheared and tangled system, of course. So we can pause and think for a moment what we're dealing with in this case. You got chains in there. They're obviously happily entangled with each other in equilibrium. then all of a sudden you decide to apply certain stress. Creep, which means apply certain stress. Right? So the language, keep in mind the powerful language we had. The language we have is stress supposedly is given by the density of entanglement strands and the force on them. We can call it retraction force. And you should quickly be able to reduce this to that in here. Because of that. Okay? So, except here things get a little tricky. Meaning, not the normal way. A normal way is we apply certain shear rate and see how I build the retraction force. Okay? Right? That's what we do normally in the rate mode. Now it's in the force mode. Stress mode. So you can ask how much, when you apply certain stress, how much of that stress is available to stretch your chain. And you can see that there is don't you think there is a critical amount, which is the cohesion force? Below which it will be balanced. So in other words, if you apply a creep under this condition, then by definition, you have a retracted, you will be able to deform your chain with a force that's smaller than this, which of course means that that this is the case. You will not destroy the structure because structure has a cohesion force of this level. So a crude way to understand the EDT is indeed, again, through, or not again, it indeed requires you to understand what is the cohesion force. I can try to I can say it in reverse. A given chain, how much it can deform, it depends on the cohesion force. It can deform a level available, which is cohesion force. And so if you externally apply a stress higher than that, then it's impossible. Because nothing can fight or can provide that much force for you. Okay, by definition, if you insist in the elastic limit, it cannot happen. So the system will just have to adopt a flow state, because it's a magic. The flow state, in theory, can sustain any stress level. You understand? Because a flow state can sustain it. When I claim that, is because I can just arbitrarily increase my shear rate. Provided, remember we said the shear thinning doesn't go with, I think normally it's, in this notation, it's Oh, I know I'm actually running out of the right notation. The basic point being that alpha is smaller than 1, so that the shear thinning never become unphysical. Okay? Because when I do that, of course, I have this as gamma dot of 1 minus alpha. And this is always positive. Yeah? And in that limit, I can, by definition, become faster in shear to satisfy the stress you applied. The elastic state is not possible to survive, just by definition. Remember, this is expression for elastic state, if you like, right? Or this is the expression for elastic state, this. So that's why eventually you have to disentangle. That's why you have, by definition, a change from entangled state to disentangled state. The definition is an entanglement-disentanglement transition. There's no controversy for that. It was hard to be accepted at the beginning. And this phenomenon, like the non-quiescent relaxation, are unknown prior to we demonstrating it in 2003. And this, of course, is in 2006. Any questions? So we are not alone on this. With all these conceptual pictures comes a more detailed theory that I will not be able to do justice, so I will not discuss, but mention that the Sussman and the Schweizer. Well, in fact, he had another guy, Shi Jie. Last name I think is Xie, and Schweizer had developed these concepts, have built a theoretical account based on such pictures that they have over a dozen papers on the topic. And the rest is really work that really should be further down is a lot more of simulations. That it just have been very difficult to perform. In part, still our computer power is still insufficient. We're still dealing with relatively less entangled systems. And in the limit, except for region 4, which I mentioned about, the entanglement is still hard to it's still fairly hard to demonstrate. The thing that I so casually draw down when you are in a just not very strongly deformed state. These such a state are still rather difficult to identify. As I keep saying, taking a snapshot does not give you any insight about entanglement or disentanglement, because it's all about whether at the junction they slide, lose force imbalance or not. So in that sense, you can say you have no way of defining entanglement, and therefore it's hard to define disentanglement. Because just the fact they have uncrossability sitting there, it doesn't tell you what it can do. Okay, I think with that, I'm closing this chapter. We will move on to the last two chapters next few times.